The problem of transferring liquid radioactive waste to a safe state is one of the main problems of nuclear energy. To minimize the radiation impact on personnel, all operations with LRW must be carried out remotely using automated control systems. The complexity of creating a unified technology for processing LRW lies in a very wide range of physical and chemical properties of radionuclides, and in differences in the type of radiation study. Perhaps the most acceptable solution for the neutralization of LRW is the immobilization of hazardous radionuclides into a solid stable matrix that will not collapse for many centuries. Due to serious shortcomings in the technology of vitrification and bituminization, as well as due to economic reasons, LRW cementing is the most preferable. However, with large volumes of LRW, it is necessary to concentrate them, separating clean water from them, and in order to optimize cementing, the salt content in the concentrated solutions should be from 600 to 800 grams per liter. The presented plant is designed for LRW concentration and cementation, has a capacity of 500 liters per hour and acts as one of the possible examples for LRW conditioning plants. The operation of the LRW solutions concentration plant does not require external sources of heat and cooling, chemical reagents, and expensive filtration materials in the form of membranes and sorbents. The main advantage of the proposed technology is that it includes a full cycle from processing the initial LRW solution to creating optimized packages of cement compound for their disposal. Moreover, the long-term isolation of radionuclides in cement blocks is ensured by the properties of shells made of bentonite clay and ordinary sheet glass. The presented plant includes a container for the accumulation of LRW with a volume of 100 cubic meters and a container for purified water of the same volume, a modular plant for obtaining a concentrated solution with a salt content of 600 to 800 grams per liter, as well as a cementing plant. The prepared concentrate is sent for cementation to the site for the preparation of a cement compound in long-term multi-layer packages. The cementing section is equipped with manipulators for carrying out all technological operations remotely. Due to the complexity of servicing pumps that pump radioactive liquids, their flow is organized by connecting tanks to high and low pressure gas environments. The system with a vacuum pump ensures the evacuation of containers, highlighted in yellow, and filling them with liquids. To organize the continuity of the concentration process, the containers in the modular plant are made in pairs. To fill one of the paired containers with liquid, it is connected to a vacuum system and, due to the pressure difference, the liquid flows into this container. All technological processes for organizing the movement of liquids are carried out remotely with minimal radiation exposure to personnel. While one of the paired tanks, when connected to a low-pressure vacuum system, works to fill the tank with liquid, the other is connected to the high-pressure system and works to empty it. All switching between the modes of filling and emptying tanks is carried out using solenoid valves on a signal from the control system, and they change functions. To empty the tank, it is connected to the high-pressure system generated by the compressor, highlighted in blue, which causes the liquid to be squeezed out of the tank. The system of automatic switching between filling and emptying modes in twin tanks allows for continuous operation in a modular evaporator plant. This modular plant, highlighted in red, plays a major role not only in the concentration of liquid radioactive waste, but also provides complete purification of water from radionuclides. Solution concentration technology using mechanical vapor recompression, MVR, solves the problems of scale formation on heating surfaces and cleaning of secondary steam from aerosols. The technology is based on the use of innovative heat exchangers, drum film evaporators, DFE, and horizontal packed heat and mass exchangers. The animation of the modular evaporator plant shows 3 DFE modules located at the top and 1 horizontal packing unit, below, designed to clean steam from aerosols. After compression ends heating in the roots pump, the steam from the steam header is sent to 3 DFE modules. In the example shown, a roots pump of 500 kg/H compresses secondary steam at a pressure of 70 kPa to 140 kPa and raises its saturation temperature from 90 to 109 degrees Celsius. This allows to use this steam as heating steam in a DFE. Each DFE module includes a horizontal cylindrical body and an internally rotating evaporator drum. The drum at the bottom is filled with the evaporating solution. When the drum rotates, a film of solution forms on the inner surface due to wetting. When the drum body is heated from the outside due to the condensation of the heating steam on the inner surface of the drum, water evaporates from the film and secondary steam is formed. The module of a horizontal packed mass exchange apparatus located in the lower part cleans the contaminated steam from aerosols. This module contains a drum packing device, the lower part of which is immersed in reflux. Purified steam from the module with a rotating annular bed of nozzles is fed through the steam pipeline to the roots pump, where it is compressed, heated and the cycle is repeated. The heating steam condensate formed on the outer surface of the drum flows into the lower part of the DFE housing. The hot condensate discharged through the thermodynamic steam trap is sent to the heat exchanger, where it transfers heat to the initial solution entering the DFE modules for evaporation. Thus, the solution enters the DFE modules already heated, which allows to increase the efficiency of the evaporator plant. When evaporating solutions with surfactants, foam may form. When the foam bubbles are destroyed, aerosols are formed that pollute the secondary steam. The module of a horizontal packed mass exchange apparatus located in the lower part cleans the contaminated steam from aerosols. The solution level in the drums is automatically adjusted using float valves. The evaporator allows the concentration of solutions to high salinity values, at which precipitates and colloidal particles begin to form. It is colloidal particles in contact with the heating surface that gradually degenerate into solid layers of scale, which impede heat transfer. To prevent the formation of deposits on surface, the heating surface is constantly cleaned with a rolling rod with a spiral wound. If it is impossible to move this rod in the axial direction, the spiral winding works like an auger, which not only cleans the resulting sediment particles, but also transports them to the concentrate discharge point. This prevents particles from accumulating in the concentrated solution and makes the evaporator resistant to scale formation. The nozzle device is a rotating annular layer of nozzles located between two perforated shells. Polluted steam entering the central part passes through a rotating layer of nozzles and is cleaned from aerosols. The nozzles polluted with aerosols during the rotation of the annular layer are periodically washed by the circulating reflux and are cleaned of contaminants. During condensation and evaporation, heat transfer is very efficient, but the presence of non-condensable gases can drastically reduce that heat transfer during condensation. To prevent this phenomenon, it is possible to periodically discharge to ventilation the gas-vapor mixture when the electromagnetic valves are opened for a short time. The presented evaporator concept was developed primarily for the processing of liquid radioactive waste, but can be used for many other purposes. When processing LRW, It allows to obtain a concentrate of optimal salt content for cementing and clean non-radioactive water. Concentrated to an optimal salt content of 600 to 800 grams per liter, the solution is sent to the mixer at the cementing site to obtain a cement compound. The resulting cement compound solution is poured into special packages with a multi-layer shell, which provide long-term protection against the release of radionuclides to the outside. After the cement compound hardens, it is covered with a layer of glass and bentonite clay, and then the package is sealed. Long-term containment of radionuclides inside the package is due to the special properties of degradation of shells made of bentonite clay and glass. Degradation of glass over time is extremely slow, while it has excellent properties in terms of leaching and preventing the migration of radionuclides into the external space. Bentonite clays, which provide sorption and waterproofing barriers and do not change their physical and chemical properties over time, provide long-term insulation of the cement compound. Filling with bentonite clay cracks that inevitably occur in glass leads to an increase in the reliability of the barrier that prevents the migration of radionuclides outside the package. Thus, the metal shell, subject to corrosion, is only a temporary barrier that serves to form the masonry from the packages of the cement compound during the final isolation of radioactive waste. To prevent the formation of salt deposits, the twin tanks are provided with constantly working agitators. To prepare the compound from a twin tank with LRW concentrate, a solution is fed into the mixer at a given flow rate. Simultaneously with the supply of the concentrate, the cement mixture is fed from the bunker to the mixer by a screw dispenser. The mixing of the concentrated mortar and the cement mixture supplied by the dosing auger is carried out in a removable continuous mixer. 3 rods with springs freely sitting on them act as mixing blades. The rods are attached to rotating cylindrical bases located in a cylindrical body with an offset to the axis of the body. The overall dimensions of the agitators and the clamping sleeves holding them allow quick replacement, and the used agitator can be placed in a package for disposal. The eccentric rotation of the rods with springs relative to the agitator body ensures constant self-cleaning of hardening cement from both the blades and the inside of the body. The volume of LRW concentrate from the tank to be emptied is designed for filling one package with cement compound. During the time of filling the tank with the next portion of the LRW concentrate, the cement compound in the package has time to harden. After the compound hardens in the package, its surface is covered with a sheet of glass using a manipulator. After applying a layer of bentonite clay to the glass, the cement compound package is covered with a metal lid and sealed by welding.